Hello, my name is Bruce. I'm a third-year PhD student at Stanford. And last summer, I was interning at Netflix, working on some work related to buffer sizing and video QoE. And today, I'd like to tell you about the results of that work. So this is joint work with Brady Walsh, T.Y. Huang, Tom Rusnak, and Joe Lawrence, who are all at Netflix, and my advisor, Nick McEwen at Stanford. So what are we talking about? So we're talking about routers, and in particular, the routers which are located at the Netflix Internet Exchange sites. So these routers are plugged into servers and ISPs. And so servers send packets to the router, and these routers, all of these routers have buffers, and these packets are put into these buffers. And on the other side, these packets are drained out of the buffers and sent to the ISPs. And so the question is, how big should this buffer be? And there's a pretty natural trade-off here. If the buffer is too big, then it is possible, perhaps during the rare times of congestion, that the buffer could fill up, and then a new packet arrives, and it has to wait behind all of the other packets in the buffer in order to be sent. On the other hand, the buffer could be too small. And in this case, it's possible, maybe again during congestion, that too many packets arrive in some instant, and if the buffer is smaller, then more of those packets are going to have to be thrown away. And so the question is, sort of like, what's the right size? So there's been a lot of work on this, and there's a very classic rule of thumb for sizing router buffers. And in particular, the rule of thumb is that a buffer should be as big as one bandwidth delay product, or BDP. And this dates back to a paper of Villemiser and Song in 1994, or an email of Van Jacobson, or all sorts. So what is this BDP? This is the bandwidth of the link times the delay of the link. And it's roughly the number of packets that can fit into the link in order to get full utilization out of the link. And so why is this the right answer for buffer sizing? Well, maybe you think there's some control theoretic explanation, or maybe the numbers sort of match up with the numbers that you work with on a link, and maybe this feels like the right answer. But in fact, the argument from this comes from a different place. It comes from the behavior of one TCP Reno flow. So here's a TCP Reno flow. On the x-axis is time. On the y-axis is the congestion window. And each point here is sort of the amount of traffic that TCP Reno is sending into the network. So just as a reminder of the way TCP Reno works, it sends a bunch of packets into the network, one congestion window's worth of packets. If they all reach the destination, it increases the size of the congestion window by 1. And it does this over and over and over again until a loss occurs. And then when a loss occurs, it goes down by half. And so how does this lead to a bandwidth delay product worth of buffering? Well, first we make an assumption about the network. And what we assume is that a loss happens when and only when the congestion window is equal to the bandwidth delay product plus B. And the intuition here is like, well, the packets, they can either go into the network or they can go into the buffer. And if there's more packets than this in the network, then where do we put them? They have to be lost. So when a packet is lost, it gets thrown away, and TCP will stop sending packets. Right. So now there's 2 times too many packets in the network. We have to throw away half the packets, wait for them to be received. And in this time period, we're not sending any packets into the network. And in particular, while we're not sending any packets into the network, the buffer at these routers is draining. And so the buffer needs to be sized sort of appropriately so that when TCP is not sending packets, that I can store enough packets. And when you work out the details of this, you go through the algebra, you find out that one bandwidth delay product is the right answer for this particular setting under these assumptions. And so there's been a whole bunch of follow-up academic work on this. So this was in 1994. In 2004, there was a paper of Appenzeller, McEwen, and Kessley that argued that, in fact, the right answer is the bandwidth delay product divided by the square root of the number of flows using that link. And this, you can imagine, is some sort of central limit theorem kind of argument where you have many independent flows and they kind of concentrate together, and maybe then the size of the buffer should shrink with the number of flows. In 2005, there was a paper of Datamir, Jiang, and Durolis, and they argued that, well, perhaps because the packet loss of TCP increases with the number of flows, maybe the buffer should also increase with the number of flows. And then finally, there was some follow-up work of Anashu, Ganjali, Goel, McEwen, and Roughgarden in 2006 that argued that under certain Poisson assumptions about the arrivals into the network, maybe you only need about 100 packets. And so there's all these different options in the academic literature, and the question we had is like, what's the right answer? We have these actual routers, we have to set an actual megabytes in these buffers, what do we set it to? And so we ran some experiments, and we found that it's actually pretty complicated. We can't tell you exactly the right buffer size for the Netflix routers, but we can tell you about some of the stuff we learned along the way. So at a very high level, this is what we learned, and let me tell you about what we learned. So first of all, we had this intuition that as the buffer gets longer, the delay goes up and the loss goes down. And we find that TCP Reno roughly behaves like you'd expect. It does this. But despite this, we learned that the effect on the video applications is not quite so clear. There seems to be a big impact in terms of the size of buffers on videos, but it's not as clean as a bigger or a smaller buffer is strictly better. And finally, while running these experiments, we learned a lot about the way routers actually work and the underlying routers, and I'd like to tell you a bit about that. So let's get started. So we're running experiments, and so we found a Netflix site. This is a Netflix site, and it's made up of a few different components. We have routers, which we already talked about, but we also have these catalog servers. And the point of these catalog servers is basically to store the entire Netflix catalog and distribute it around the world. There's also these offload servers, and the point about offload servers is to offload traffic from the catalog servers and serve approximately the top 30% of content as quickly as possible. And so these are very optimized servers to quickly serve content. So together, these three racks are called a stack. And a Netflix site is usually made up of two stacks. There's an A stack and a B stack. And these are for fault tolerance and reliability and stuff like this. And so we found a site where traffic was being randomly assigned to the two stacks. And we found the two routers, and we made one buffer small in one of the stacks and the other buffer large. And we looked at the difference between the two. So this is what we found. So for TCP Reno, here's a graph. On the x-axis here is the minimum round trip time. And what this means, we look at a TCP connection, we look at all of the packets in that TCP connection, and we look at the minimum round trip time over all of those packets. And then we looked at all of the sessions during one congested hour, and the y-axis here is the fraction of sessions which had that minimum round trip time. This gray distribution here, this is during an uncongested hour, the distribution of minimum round trip times during an uncongested hour. The blue line here is for the A stack during a congested hour, which had a 50 megabyte buffer. So you can see the latency sort of increased by about 30 milliseconds. And the orange line here is the B stack. This was, we set the buffer to 500 megabytes. And here the latency increased by about 90 milliseconds. So maybe this is sort of not shocking, but as the buffer size got larger, the minimum round trip time went up. Sometimes, though, so this is a different site, a similar experiment. We set the A stack to 3 megabytes, the B stack to 500 megabytes, and we looked at what happened. So this time the A stack, again, saw a bit of an increase in latency, but the B stack, there was some weird behavior. It did get a lot larger latency, but the latency was a lot more spread out. Like here, if you look before, it's just sort of, the buffer is constantly adding some delay, but here it's adding a variable amount of delay. So we'll get into why this is in a little bit. But maybe just for now, we can take it that the larger buffer still has higher latency. So also, we expect the larger buffer to have less loss, and this we found was true. So what this graph shows on the x-axis is the normalized load. So each point here is an hour, and the x-axis is the load for that hour as a fraction of the most loaded hour. The y-axis is the fraction of bytes that were retransmitted during that hour. And as you can see, as the load goes up, at some point we start to see congestion, and there starts to be more loss. And what we see is that the loss happens sooner and more severely for smaller buffers. So for a 50 megabyte buffer, say, at about 70% loss, at 70% load, we start to see an increase in retransmits. And this is much larger than for the larger buffer. So things are behaving as expected so far. But another thing we found is that the effect on the actual video application, which is the stuff that Netflix cares much more about, it's not quite so clean. So what we found is that there's good buffer sizes and there's bad buffer sizes, and basically good buffer sizes are good for video and bad buffer sizes are not. And with the good buffer sizes, we see fewer rebuffers. So these are these times when you're watching the video and the video pauses and waits to be downloaded. We see fewer of those with well-sized buffers. We see improvement in the actual picture quality of the video that you watch. And we see videos start faster, so less delay to actually play the video. And bad buffer sizes, the opposite of that happens. But what we observe is that the bad buffer sizes, this can happen both when the buffer is too large or too small. So let me show you some examples. Here's a particular site. We ran an experiment where we reduced the buffer from 500 megabytes to 25 megabytes. And over all of the congested hours during this experiment, this is what we observed. We saw a 15% decrease in rebuffers, a 5% decrease in the sort of time of poor video quality, and a 13% decrease in play delay. And these were all like really big improvements by decreasing the size of this buffer. Here's another site. We ran another experiment. We reduced the buffer from 500 megabytes to 50 megabytes. And again, we saw really big improvements. We saw a 20% decrease in rebuffers and improvements in all the other metrics too. And so at this point, you might be thinking, we should just set everything to 50 megabytes, but this was not true. And we ran another experiment in another site, reduced the size of the buffer from 500 megabytes to 50 megabytes, and everything got worse, basically. We saw a huge increase in sessions with rebuffer, like 45%, an increase in the fraction of bad quality video, and there was a bit an improvement in play delay, but it certainly wasn't enough to pay for the rest of that. So the point of all that, it seems like buffers really matter for video performance, but the actual buffer size that we were setting was not quite so clear. And so let me call back to before. So remember we had these latency distributions. And in this case, we saw a larger buffer just added like a sort of fixed amount of latency. But in this other site, we saw a much more variable latency. The larger buffer really added a lot of variation to the latency. And so it was really sort of surprising to us of what was going on here. So we started digging into it, and we made this graph. And so what this graph shows, each row here is a server in the site. They're all going to the same router, all over the same link. And it's the latency distribution for that server for a congested hour. And so what you can see is that all of these servers have wildly different latency distributions. It's all over the place. And to me, this was super surprising, because remember, we're talking about one router here. We have a bunch of servers. They're all plugged into this router. And this router, I imagined, it has a buffer. And maybe the reason I imagined this is because when we were reading these papers and learning about buffer sizing and how it works, we always drew this picture of like one buffer in the router. But if there's only one buffer and all the traffic is going over one buffer, how can it be that all these servers have different latency distributions? Like, it didn't make any sense at all. And so what we discovered, talking with our vendor, this is not at all true. This is not how routers work. And so let me tell you about how routers work. So we have these routers, and routers have line cards, and these line cards just sort of slide into the front, and they have a whole bunch of ports on them. And these ports are split up into VOQs, or virtual output queues. And these just sort of correspond to physical ports on the device. So here I've just drawn 8 VOQs. This may not be the actual VOQs here, but let's say there's 8 VOQs. Internally, things look something like this. You have 2 VOQs, in this case. Servers are plugged into the VOQs, and servers send packets. So packets come from the servers, they go into the VOQ, and then later on, the port has to pick some packets from the VOQs and send them out onto the actual link. And so, the link needs to pick some packets, and it needs to choose some way to do this. And so the way it does this, at least when we were running these experiments, is it looks at the number of ports which are plugged into the VOQs, and it sort of fairly splits the traffic based on that. So just as an example, if everyone sends 40 gigabits per second into the VOQ, then in this case, the top VOQ has 2 servers, will get 2/3 of the output port. The bottom one has 1 server, it will get 1/3 of the output port, and everything seems fine. But suppose, on the other hand, that this bottom server only sends 10 gigabits per second of traffic. Then from the switch's perspective, and it has to do the scheduling, this bottom server isn't sending its fair share worth of traffic, right? It's not sending 33 gigabits per second, it's sending less than 33 gigabits per second. So what the switch did in this example is it just let all of the traffic through. It added no delay to this one VOQ, and it put all of the delay onto the top VOQ. And so in effect, the switch was prioritizing the traffic of the bottom VOQ. If we go back to the example from before, we can see that this explains what was going on. So this is the same graph, each row is a server, but this time each row is colored by the VOQ that it belongs to on the switch. And what you can see is that within one VOQ, the latency tends to be the same, but across VOQs, the latency is very different. And this is because the scheduling algorithm is giving different priorities to these different VOQs. So for instance, this purple VOQ in the top left, this one is served much faster than this orange VOQ on the right. Here's another example of what we saw. So each row, so this is one site. Each row here is the distribution of latency for an hour in that site. This middle row here, which is labeled with 0 on the side, that's the peak hour. And then above it and below it are hours before and then after peak. So as the site begins, and it's not yet in peak, everything has the same latency, and there's no congestion. But there's two lines here, and the line correspond to these catalog servers and these offload servers, or the long tail content and the more popular content. And as the site comes into the peak, the popular content is the one that gets congested because of this underlying scheduling algorithm in the router, and the long tail content is not congested at all. And so this was really surprising to us when we saw this, because maybe Netflix as a business has some priorities about how this traffic should be served. And here the actual router deep in the scheduling algorithm was making the choices about what of these types of content was more important. So we've been working with our router manufacturer on different ways we can try and improve this situation. And we've been testing, these are very preliminary results, but we've been testing a new scheduling algorithm. So it's similar to before. Again, we still have these VOQs, but this time, instead of just splitting the traffic based on the number of ports which are up, we're splitting the traffic based on the amount of load that these ports are offering. So if this top VOQ is offering a lot more load, it should get more share of the output link. And there's a second change, which is that the sizes of the VOQs we can now adjust to target a particular global latency across the VOQs instead of setting each of them individually. So with this, we see improved results. So these two graphs, the top one this is the same hour, the same site. The top one is with the new scheduling algorithm. The bottom one is with the default scheduling algorithm. With the new scheduling algorithm, we see more consistent latencies across all of the servers. It's still not perfect. There's still a few servers that have sort of not the same latency as the rest of them, and so we're still working with our router manufacturer to improve things. But certainly, I mean, look, the latency is 60 milliseconds down from 500 milliseconds of buffering, so it's definitely an improvement, and the variability is lower. So just to summarize, we ran some experiments where we looked at different buffer sizes, and we found some stuff. What we found was that TCP new Runo mostly behaves like your intuition would suggest, where the larger buffers have less loss and higher delay. But despite this, what you actually care about, or what we care about, for the performance of video, this was not quite so clean. The size of the buffer matters a lot for video, but there wasn't an exact buffer size which was right for video. And finally, the way routers actually work made this a bit more complicated to understand, because if there's all of this underlying scheduling algorithm stuff going on, what is even the capacity of the link for a particular VOQ? We didn't know. So this brings us back to our original question. We tried to answer this, and we learned a whole bunch of stuff along the way of doing it, but we're not going to be able to tell you exactly how big a buffer should be. We can't tell you this for Netflix, and we're certainly not going to be able to tell you for your network. Because look, you have different traffic, you have different routers, you have different things that you care about in terms of metrics. And so what I'd invite you to do is to go and run this experiment for yourselves. You have routers, and these routers have buffers, and you could change the size of these buffers in these routers and look at what happens. And so maybe you could change it a little bit, and if things get better, well, you could change it a little bit more. I think if you did this, you would find some really interesting and really surprising things. For me, I was really surprised by this underlying scheduling behavior of the router. And maybe there's other stuff like this which is going on in your network. At Stanford, we've been running a workshop on buffer sizing, and we're considering running another one next year. Mostly if we had people who are interested in running experiments and sharing some interesting results. So if you do run these experiments and you do find something interesting, I would really love to hear about it, and I think we as a community would really love to hear about it. And maybe we could answer this question of how big should a buffer be. So that's it. Thanks. Any questions?
Excuse me. Yeah, a quick question. Could you go back to the slide where you're showing the 100 gig output split to 90 gig and 10 gig?
No.
I guess what I'm wondering is the...
Okay. 90 and 10, yes, this one.
Yeah, wouldn't the pathology be rather that so much is focused on that first slot of ports rather than being randomly distributed across all of your slots?
Mm-hmm. So you're saying maybe this is the fault of the way things are wired up?
Yeah, I was assuming that all connections would be coming in at some degree of randomness so that you'd have a natural scattering of flows across all of your ports and all of your blades equally.
Right. So this was just corresponding to the way that there was these two different types of servers and the way these were plugged into the switch or the router. And we didn't want to fix this by going and re-cabling everything. This seemed like a lot of work. and not clear that it would like actually fix the problem.
Hi, had a question on the overall outcome. So it sounded like it was going to be like a global default fix for VOQ and then some tactical usage on the buffer updates. So what was the overall outcome?
I guess the outcome is we've been working on this new scheduling algorithm. We're testing it out, seeing if it works better. So we came up with a way of running an experiment where we can tune the buffer size, and so we may do that. But it would definitely be nice to come up with an actual number.
And so the VOQ updates, as far as changing the defaults, was that everywhere or just certain places?
No, this is like, we're still testing it.
Okay.
Hi, Tony Tauber, Comcast. I'm wondering, so for your situation, you're dealing with the router and the server, and you've got total visibility to both. So those latency measurements are taken at the server. Like, what was the methodology on that part?
Yeah, so those latency measurements are measured by TCP. It's between the server and the client.
Okay. So, right, you have to be on the host that's got that. Okay.
Yeah.
So, yeah, I'm just trying to think of how it would apply to us. Okay, thanks very much.
Yeah, I guess the measurements were from the host, but like, I mean, you can sort of look at this, and when there's no congestion, like the latency is pretty small, and when there is congestion, it's huge.
Yeah.
So it should mostly be on the router, and you can probably measure that if you have a router.
Thanks.
Yeah.
Julie Egley. Funnily enough, I have a ticket to do the same measurement that you have. I've just been sitting on it for about a year since I did a presentation at your little shindig. But I guess one of the questions I would ask is, yes, new scheduling algorithm, but have you also compared Reno to BBR in this same context? And in particular, like, because this is video streaming as opposed to, say, trying to deliver objects as fast as possible. Like, it seems like there are a number of things other than the buffer size that people are playing with. So packet pacing is one of them, because why not schedule things when you send them? But yeah, I mean, comparison to BBR and your new SCIT algorithm seems like a place that people are jittering the options in addition to playing with the buffer size, right?
Yeah, totally. So I guess the broader point is like there's a lot of different algorithms that wind up sending traffic, and all this traffic goes over the buffer. And so we should be able to change the algorithms and change its effect on the buffer, which is true. We started looking at BBR. I don't think we have any sort of conclusive results about it, but it seems like it should matter.
Yeah, I mean, there's the other piece of this, which is like Netflix and I are both CDNs, and so we sit in a particular place in the network, and our traffic mix is sort of self-selected, and other people don't get to decide necessarily what's in their queue or what order it arrives in. So, like, I'm obviously very interested in everything you do because it directly impacts my work, but I have a little trouble sort of generalizing it to like, what should I buy as an ISP in order to serve like my customers, some of whom's applications look like this and some of them look like Zoom or whatever, fairly. And I think we're not super great yet at describing what that looks like for the rest of the world.
Yeah, I agree. I don't think we have a clear answer for like what the hardware is, and it would be lovely like to see some experiments maybe from ISPs where we could look at this.
Hi, I'm Narayanan. I work for Arista. So when you mention 25 meg or 50 meg or 500 meg, this is the amount of buffer assigned to per ingress packet processor or per port, per traffic class? What exactly is this?
This is the amount of space assigned to one VOQ, which I think is per traffic class.
All right. Okay.
Yeah.
Thank you.
So the scheduling algorithm, is that run consistently or on a scheduled basis? And have you seen that affected by hardware or software upgrades to the routers and/or servers?
So the question is it sort of run continually or is it sort of outside of the router? It's run continually. I think it runs on the router. This adaptive one runs on the order of every couple seconds, I think. And this previous one was run like every packet. So it's not affected by the other stuff. Great. I guess no more questions. Thank you.